Good afternoon, sir.
Good afternoon, sir.
Okay, so in last class we started our discussion about vectors. Okay, so some of you are already familiar with vectors, and basically their representation in the matrix space. Okay, so basically it is a point. It's some collection of basically data. Okay, the vector is nothing but collection of data. So data basically it's represent the point, okay, the tip of the vector. Okay, and we always consider that ground means basically the origin is at center, means 0 0 0. Okay, so that's why it is always possible to represent any vector using our you can say column vector or in terms of row vector. Okay, so or basically matrix vector. Okay, so why it is possible? Because we always consider that that vector is basically representation of this point, and with respect to our center always at 0 0 0. Okay. And we have seen that any vector in two-dimensional space or three-dimensional space can be represented as linear combination of the basis vector. Okay, so basis vector basically represent the vector in orthogonal, let's say for example x, y and z coordinate. So one vector is in x direction, one is y direction and one is z direction. Okay, and if you put that weighted sum of them, so then you will get a particular vector or particular point in the space. Okay, and then later on we have seen that how to represent the matrix representation of vector. So we have studied that one, and then what we have studied that is basically transformation of vector. Okay, so how one vector can be transformed into another vector. Okay, so that thing we have studied. Okay, or basically we can transform the coordinate system itself. Okay, so we can transform the coordinate system itself by certain rotation. Okay, so or basically some changing. Okay, so by changing the, you can say by multiplying the basis vector, by multiplying the basis vector we can form another sets of basis vector. Okay, so this is the modifier or you can say the transformer. Okay, the M matrix is basically the transformer or the modifier, so which basically modify our coordinate system, or also it can modify any vector on that space. Then we have studied about the translation of coordinate system, that you can translate the origin. Okay, you can translate the origin of a coordinate system and make a new coordinate system. Okay, so the origin has been shifted, and based on the new origin you can redefine a particular vector in the with respect to the new origin. Okay, so in that case it is basically the original vector minus the shift in origin. So that is basically, in previously your original origin was in 0 0, now it has been shifted to 1 and 2. Now we can see that is basically 1 1 vector. Okay, okay. So we have not discussed about the scaling in the last class. Did I discuss about scaling of vector?
No, sir.
No, sir.
No, sir.
Okay, so scaling is basically you are basically multiplying. You are multiplying the vector, basically each coordinate. Okay, so you are multiplying the vector by a certain amount. Okay, so that is basically scaling of the vector. So for example, you have a 1 1 vector. Now you can scale that 1 1 vector by, let's say by 2, then it will become 2 2 vector in the same coordinate system. Now what we are trying to study, the scaling of the coordinate system itself. Okay, so we have a unity coordinate system, let's say fundamental basis, let's say x and y. So these are two fundamental bases, but I want to scale the x by 3 and y by 2. Okay, so that become our new coordinate system. So if I do so, then S is my scaling matrix. S is my scaling matrix, and you can see it is a diagonal matrix. The scaling matrix is always a diagonal matrix, that is 3 2. Okay, so it is a diagonal matrix. So it is basically represent the scaling of x, and this is basically represent the scaling of y. So in the other way you can view, so if you take, this is the slice. So this is slice. So this is basically 3 0 represent x and 0 2 represent basically y. Okay, y prime. So this is x prime and this is y prime. Okay, now you can say that x prime is can be obtained by multiplying s with x. Okay, x is my original basis vector and this is my new basis vector, and similarly y prime can be obtained by multiplying the scaling with respect to y. Now you can see that in the new coordinate system, so in our original coordinate system, we can write down our point, let's say our vector, that is 2, 3. Now in the new coordinate system, our vector value are basically, vector is basically 2/3 and 3/2. Okay, so why 2/3 and 3/2?
Since now the axes have gotten bigger, so the component will be small.
Yes, the component. So basically, when we will write v prime is basically this. These are the coefficient. Okay, coefficient into the basis vector. So now my new basis vector is basically this one. So if you take the system is basically this one. So if I multiply this with the system, then I will get the same result. Okay, if I multiply this with the system, then I will get the same result as 2 and 3. Okay. Okay, so the same thing has been explained here. Okay, how you are getting 2 and 3. Okay, it is basically S inverse of V. Okay, so in that way you can easily find out that what is the new vector in the new coordinate system. That's the same vector in the new coordinate system. Representation of the same vector in the new coordinate system. Okay, so this is very important property, that is rotation of coordinate system. Why it is important? Because we need to deal with the Cartesian coordinate, cylindrical coordinate and spherical coordinate. So those coordinate, new coordinate system are basically rotation of one coordinate system with respect to another one. So we'll see later on. Okay, so that's why this rotation matrix is very important. Now consider you have original system, that is basically x and y. So x is basically 1, 0 vector and y is 0, 1 vector. Now I want to rotate this coordinate system by 30 degree. So I want to rotate, so just rotate the coordinate system by an amount of 30 degree. Now with this rotation you form a new coordinate system, that is x prime and y prime. Now I want to find out what is x prime and what is y prime. So that is basically multiplication of the original x with respect to our rotation matrix. So rotation matrix into x. Okay, so this rotation matrix is basically cos theta, sin theta and minus sin theta and cos theta. Now why it is? So you can see, so one thing you can observe, that if I rewrite this, let's see. Need to observe this one, that is basically, so I have shown you in the last class also, that is x prime and y prime. So this is basically two vector. So x vector, x prime vector is equals to your rotation matrix R into this is basically 1, 0, x is 1, 0 and y is 0, 1. So it is basically identity matrix. If you multiply identity matrix with any matrix, that is basically same matrix. So basically x prime and y prime is nothing but the rotation matrix. Okay, so that rotation matrix is, let's write down, that is basically cos theta and sin theta, and here minus sin theta and cos theta. Okay. Now you can see, so this is my x prime and this is my y prime vector. Okay. So here you can see that why it is cos theta and sin theta, because take the component in the x direction. So if you take, so this angle is theta, then the component of x prime in the x direction is how much? If I take projection of x prime on x direction, how much is cos theta?
Cos theta.
And similarly, if I take the projection of x prime in the y direction, that is basically sin theta. So that's why it is cos theta sin theta. And the y prime, so if you take the projection of y prime in the x direction, how much? So this is theta. This angle is theta. So if I take the projection, minus sin theta, because it is in the negative x-axis. Okay, so that's why minus sin theta. So this is theta. So this is 90 minus theta. So if you take the projections, that is basically minus sin theta, and the projection in the y direction is basically cos theta. So that's why the rotation matrix is something like this. Okay, so this is the reason why rotation matrix formed by having this you can say property. Okay, so how this rotation matrix is formed. Okay, now this matrix play important role in the coordinates transform. Okay, so we'll see later on. Okay, so this is basically representation of the same vector. Okay, so you have a original vector that is basically 2, 3 in our original code with respect to our original coordinate system, but with respect to the new coordinate system, how this vector change. So that is basically same rule is applicable. So you need to write that V is basically x prime y prime into ax prime and ay prime. So these are the coefficient. Okay, so our coefficient is basically the by v vector. Okay, so this is your R matrix, the rotation matrix into the v prime vector, and from here you can solve it. That is v prime is nothing but R inverse of v. Now you can see that rotation matrix having a very beautiful property. So what is the property? So can you observe that? What is the property?
Adjoint, inverse is adjoint.
Yeah, inverse is transpose. Inverse of rotation matrix is basically transpose. It is the transpose, na?
Yes, sir. Yes, sir.
Okay, so it is the very beautiful property. So another you can say this type of property. Let's say for example eigenvector. So eigenvector of a real matrix having the similar property. Okay, eigenvector of a real matrix having the similar property. They are orthogonal. So you can say this matrix is basically or you can say these vectors are basically orthogonal to each other. These vectors are basically orthogonal to each other. Okay, so that's why they possess this property. Okay, the inverse is basically equals to transpose when they are orthogonal. Okay, or you can say this matrix itself is basically orthogonal. Okay, now if you do this multiplication, then you will get the representation of the same vector in the new coordinate system. Okay, so this way we can do so. Okay, now it comes to coordinate system and its transform. So what are the coordinate system? So the first coordinate system is Cartesian coordinate system. So it is well known to you. So in the Cartesian coordinate system, so you have a, let's say, certain point is there, P. Now direction of x is basically in the direction of x direction. Okay, and direction of y is basically in the y direction. Direction z in the z direction. Now here it is very important. There are two things are there. One is the direction vector. One is the direction vector. So x direction, y direction, and z direction. So direction vector. And another thing is that the point. This point. Okay. So this is basically coordinate variable. X, y, and z will call it as a coordinate variable. X, y, and z will call coordinate variable, and this direction are basically different. So we'll see later on that what is the difference between coordinate transform and coordinate variable transform. So these two are two different things. So sometimes people get confused that coordinate transform and coordinate variable transform. Okay. So when we talk about the coordinate transform, means basically the vector transform. How the vector represented in the new coordinate system. Okay, it's the same vector. And when we talk about the coordinate variable transform, basically transforming this variable from one coordinate system to another coordinate system. Okay, so we'll see later on. Okay, how they are different. Now you can say that any point V or any vector V in this coordinate system can be represented as ax, ay, and az. Okay, and these are the corresponding direction vector. Okay, so these are the corresponding direction vector. So you can write either in this form, column vector, or you can write in this form. Okay. Now the next coordinate system is cylindrical coordinate system. So in the cylindrical coordinate system, so how this direction are defined? So that thing you need to understand. So in the cylindrical coordinate system, let's say you have a point P. You have a point P, and P having three things. Okay, one is rho, okay, so rho, phi, and z. So these are basically coordinate variable. Please note that these are coordinate variable. Okay, not coordinate vector. These are basically coordinate variable. Okay, and the vector are basically a phi. So it is basically instead of writing a phi, I should write it's basically phi direction. So okay, so I think I rewrite here. Okay, so I think it was directly taken from book. So there they have used this notation. So okay, so you can see this direction phi is basically represent the tangent of this cylindrical surface, and it is in the xy plane. The tangent of this cylindrical surface in the xy plane. Okay, and rho is basically normal. Rho is basically normal to the cylindrical surface. So we have considered a hypothetical cylindrical surface, considering that point is on the boundary. The point is on the boundary of this surface. Okay. Now here you can see the z is basically similar to our original z, and rho is basically the normal. Rho is basically normal to our you can say this cylindrical surface. Okay, so rho is basically normal to the cylindrical surface. Now here you have to understand that how this xyz and this you can say rho, phi, and z. So this coordinate has been transformed. So you have to understand. So that is basically you can see that if I do some rotation. So let's say this is my x. So this is my x, this is my y, and this is my z. Okay. Now if I let's say here this way it was there. Now if I rotate further that x by a certain amount phi. If I rotate x by certain amount phi, then you can say that x will point towards the rho direction. The x will point towards the rho direction, and y will point towards the phi direction. So basically you can say that this from the Cartesian coordinate to cylindrical coordinate is basically rotation in the so basically rotation with respect to your z axis. So it is basically rotation with respect to z axis, and the amount of rotation is equals to phi. The amount of rotation is equals to phi. Okay, so the phi is basically defined by this point. Okay, this phi, that amount of rotation, that is basically defined by this point. Okay, where is this point is located. Okay, so how to find out the phi value? So we'll see later on. Okay, how to find out the phi value from x, y, and z value? So we can see later on. Okay. Okay. Now the next coordinate system is basically the spherical coordinate system. In the spherical coordinate system, we consider that there is a hypothetical sphere. So there is a hypothetical sphere that is basically enclosed this point P. So you have a particular point P in a coordinate system, and this hypothetical sphere basically just close basically on the surface of that hypothetical sphere. Okay, this point P. Now in this coordinate system, the direction r is basically the normal to the surface. The direction r is basically normal to the surface, and direction theta. Okay, so direction theta is basically, so before that let's say what is phi. Okay, so the direction phi. So do you have a good graph? I don't have. Okay, the 3D graph. Okay, so this direction phi is basically same as this one. You can imagine. Okay, so this direction phi is basically same as this one. Okay, and direction theta is basically if I rotate this. Okay, so if you think this you can say coordinate system. This coordinate system is rotated with respect to phi axis. This coordinate system is rotated with respect to phi axis. Then the rho will point towards r. The rho will point towards r, and z will point towards theta, and z will point towards theta. Okay, so in this way, your new coordinate system has been established, or the vectors in the new coordinate system. Okay, or basically the direction of the vector. So Okay, so now it comes to coordinate variable. Okay, so you can see that coordinate variable rho, phi and z can be represented by x, y and z as rho is equals to square root of x square plus y square, and phi is equals to angle x plus jy. Okay, angle x plus jy. So it is very, as I have told you, that instead of taking tan is not good, instead of taking the tan inverse y and z, it is not good. So we can write in complex form an angle of that. Okay, so that is a good way to represent the angle, and z is equals to z. Okay. Now the inversely, the coordinate variable x, y and z can be obtained, okay, or can be obtained or can be represented by rho, phi and z as x is equals to rho cos phi, y is equals to rho into sin phi, and z is equals to z. Okay. And coordinate variable r, theta and phi can be represented by rho, phi and z as r is equals to rho square plus z square, theta is equals to angle z plus j rho, and phi is equals to phi. Okay, so phi is not changing. So the meaning of phi here and in the spherical coordinate and the meaning of phi in the cylindrical coordinate are basically same. Okay, they are not different. Okay, so inversely, the coordinate variable rho, phi and z can be represented by r theta phi as rho is equals to r sin theta, phi is equals to phi, and z is equals to r cos theta. Okay. So in this way, we can change one coordinate variable to another one. Okay. Now see that another relation remain, that is basically cylindrical to Cartesian or Cartesian to cylindrical. Okay. So from the Cartesian to cylindrical can be Cartesian to spherical. So from Cartesian to spherical can be obtained by this way. So r is basically the you can say this radius. Okay, so the x square plus y square plus z squares, or you can say it is the Euclidean distance. It is basically Euclidean distance of that point. Okay, and phi is equals to angle x plus jy. Okay, so it is basically angle x plus jy, and theta is equals to z plus j square root x square plus y square. And in an inverse way, we can write that x is equals to r sin theta cos phi, y is equals to r sin theta sin phi, and z is equals to r cos theta. Okay. So in this way, you can change from one coordinate variable into another coordinate variable. Okay. So this is the change of, or basically transformation of, coordinate variable. Now we'll see about the transformation of coordinate system. So these two are different. Please note that the transformation of coordinate system and transformation of coordinate variable are different. I don't know whether you are getting or not. So are you getting this one or still have doubts? Please let me know.
Getting, sir.
Okay. Okay, so now we'll do Cartesian coordinate system to cylindrical coordinate system. Okay, so how to obtain that one? So as I told you that cylindrical coordinate system is nothing but rotation. The cylindrical coordinate system is nothing but the rotation of the Cartesian coordinate system. The cylindrical coordinate system, the vectors in the cylindrical coordinates are basically the rotation of the vectors in the Cartesian coordinate. Okay, so this is the coordinate transform. Okay, so basically you can say that this is basically vector transform. So you can see. So let's say this one, this is my x. Okay, this is my x, this is my y, and this is my z. So if I rotate it, okay, if I rotate it the phi amount, then I can get the vector in the new system. Okay. So please note that here, in cylindrical coordinate. In cylindrical coordinate, the definition and the direction of the phi vary. The definition and the direction of the phi vary from point to point. The definition and the or you can say the direction of the phi vary from point to point. For different point, it has different value or different direction. Please note that one. And same is true for the rho. Do you agree or not? Let's say I draw the, you can say here. I want to find out the vector of the cylindrical system here. So the direction of rho is not same. So here the rho is basically this way, it is pointing, but let's say you have a cylindrical surface like this. Okay. So from at one point it is pointing this way and another point is basically pointing this way. Okay. So are you getting this one?
Yes, sir.
Yes, sir.
Okay. So basically at different point, that rho will be different. Okay. It is not that, for example, Cartesian coordinate system, it is universal. For Cartesian coordinate system, it is universal. So whatever the point, the z direction will be z direction, the x direction will be the x direction, and y direction will be y direction. But for cylindrical coordinate system, that direction of rho and direction of phi is basically depends upon the position where we are measuring. Okay, it basically depends upon the position where we are measuring the vector. Okay, so please remember this one. Okay, so you can understand it is basically a rotation of Cartesian coordinate system by phi amount, and that phi is also depends upon the where the point is located. The phi basically depends upon the where the point is located. Okay. Now this phi is basically depends upon the where the point is located, and to find out this phi, what you have to do? Let's say I am giving you it is very important thing. I am giving you one vector, let's say electric field. Okay, we have a electric field vector E. Okay, electric field vector. Let's say it is. Let's write in matrix form. Let's say it is 3, 2, minus 1. It is the electric field vector. Okay, so it is Ex, Ey, and Ez. Okay, in Cartesian coordinate system. Now I want to find. So it is at point. It is. This is the value at point, because field is function of space, na? The field is basically function of space. So it is at the point, let's say, for example, 1, 1, 1, 1, 1, 1. Okay. So what is this? 1, 1, 1? It is basically x, y, and z. So this is basically your position variable, x, y, and z. This is the position variable. Okay. And this is basically Ex, Ey, Ez. Okay. Now I want to transform this electric field from the Cartesian coordinate to cylindrical coordinate. So for that, at first I need to find out the phi. How to find out the phi? What is phi here? Hmm?
45.
45. So that is basically angle 1, 1 plus 1j. 1 plus 1j. So that is basically 45 degree. Okay, so phi is 45 degree. Now, once you know the phi, it is 45 degree, then you can form the, you can say this one. So you can form the coordinate system. Oh, sorry, the rotation matrix. So you know what is phi. So then you can you know that how to find out the rotation matrix. Now please note that this rho, phi, and z. So these are the unit vector. So this is the basically unit vector in the cylindrical system. So these are the basically unit vector in the cylindrical system. Okay. 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 So we'll see about the vector transform, how this vector transform, how it is different. Okay, so vector transform and the coordinate system transform, this is basically a little bit different. Okay, so you have to be very careful here. Okay, now this x has been rotated by phi amount with respect to z axis. Okay, and you can see that this is basically the same rotation matrix. This is the same rotation matrix what we have discussed in the earlier, that rotation in the xy plane. Okay, and the amount of rotation is phi. Now you can see, so it is basically, if I multiply this 1 0 0, so it is basically a slice of this one. So this slice is rho, and this slice is basically phi, this slice is phi, and this slice is basically z. Z is basically 0 0 1. Okay. Now this is basically my rotation matrix. Okay, R phi is basically rho, phi, and z. Okay, this is the rotation matrix. Now if this is the rotation matrix, then Ax, Ay, Ag is basically this rotation matrix into A rho, A phi, and Az. So it is basically E rho. So let's say if we consider that it is electric field, so it is the E rho, E phi, and Ez. Okay. Then for this, what you have to do? You have to do the basically inverse of this. If you do this inverse, so this side, then if you multiply, this is Ax, Ay, and Z, or you can say it is Ex, this is Ey, and this is Ez. And if you multiply, then you will get the value of E rho, E phi, and Ez. Ez obviously it will not change. Let's do it. Okay. So my E rho, E phi, and E z. Okay, obviously Ez will not change, and only rho and phi will change. Okay, so that is equals to, what is cos phi? That is obviously all them will be 1 by square root of 2. So here you can write 1, and what is sin phi? That is also 1. Here -1. Here 1, 0 0 0 0 1. Okay. Now if I multiply 3, 2, -1, what you will get? So that is 1 by square root of 2. So that is 3 plus 2 is 5. Get 5, and then -3 plus 2. So that is -1. And here you will get -1. You will get, okay, so here I'm getting, so it is basically square root of 2. Yeah, I'm wrong. Okay, because if you multiply this, then you will get 1. Nah? So this value is 1. So this is basically, if you do this multiplication, then you will get minus square root 2. So that is basically 5 by square root 2, that is -1 by square root 2, and here we'll get -1. So do you have any doubt? Hmm?
Yes, sir.
So you have understand the process now, how to find out that, let's say, how to transform one vector. Let's say, for example, you have an electric field vector in a particular point 1 1 1 1. So that has been transformed into cylindrical coordinate system. Okay, so these are the basically E rho, E phi, and Ez in the cylindrical form. Okay, any doubt? If you have any doubt, please let me know. So I will try to re-explain. because this understanding is very important. When you try to visualize electric field in 3D space, so this concept is very important. So all of you are getting this one, or if you have any doubt, please let me know.
Yes, sir, understood.
Okay. Okay, so that's good. So you understand the process that how to transform the vector from one coordinate system into another coordinate system, and also please remember here, so it depends upon the position. Please remember that this transform basically depends upon the position where you are, that at which position you are transforming the vector. And also another thing is that basically it also depends upon the origin. It also depends upon the origin. So because let's say your origin change, if your origin change, then all the definition and basically it is a relative thing now. So all the things will get changed. Okay. So that's why sometimes this subject is a little bit difficult. Many people find it
Then
difficult. Yes.
if instead of 1 1 1 we had position of 0 0 0, then how would we find phi?
Okay, so in that case, yeah, it is a good question. That if it is 0 0 0, okay, so if it is 0 0 0, then how to find out phi? So in that case, I think it is not possible. If it is 0 0 0, then it is not possible. Okay, because in general we don't measure. Let's say, for example, let's say. Uh, in general, we do not, I mean, basically it's basically become a singularity kind of thing. So we will not able to get that what is the direction, because it is possible that direction of electric field may be in the all direction. It is very difficult to do. Okay. So because it is basically a little bit undefined, because you cannot define the phi. So all the possibilities of phi are possible, but if it is a little bit distance from the origin, then you can determine. Okay. Okay, so next is cylindrical to spherical. Okay, so we are going step by step. Now, in case of uh, here, okay, so we have done this one. Now from cylindrical to spherical. Okay, so for that, what we will do here, it is basically kind of another rotation. So it is the rotation. So you can see, so this is the rotation. So this R, okay, so this phi, okay, so this phi has been, sorry, this rho has been rotated by angle theta. So this rho is rotated by an angle theta, and this z become R. This z become R. Sorry, in the previous case I told you wrong. Okay, so this z become R. Okay, and this rho become theta. This z become R and this rho becomes theta. So this way it is rotated. Okay, so in this way. Okay, so you can see this z become your R. So this z become R, and your this thing rho become theta. Okay. So this thing has been happened. Okay, so for this your rotation matrix is something like this. Okay, so it is basically rotation of phi axis with, so rotation with respect to phi axis, and amount of rotation is theta. The amount of rotation is theta, and this is the basically rotation matrix, overall rotation matrix. So overall rotation matrix is formed by r vector, theta vector, and phi vector. Okay, so there is r, theta, and phi. So if I write this, so it is basically something like this. So it is sin theta, cos theta, and cos theta minus sin theta, and this is 0, so 0, 1, 0. Okay. Okay, so this is the relationship that R A rho, A phi, and A z is equals to rotation matrix into AR, A theta, and A phi. Okay, and from this you can form the inverse relationship, that is basically AR, A phi, A theta is equals to inverse of this. So inverse of this is nothing but the transpose of this matrix. So inverse of this is basically transpose because it is orthogonal matrix. Okay, and by multiplying this with respect to this one, okay, this rotation matrix, you will get your value of new, you can say value of the vector, okay, or you can say the amount of vector in a particular direction for a particular point. Okay, so in this way you will obtain. Okay, okay, so that's fine. Now another problem I did not discuss here. Let's say I have to do the inverse transform. So for the inverse transform, what you will do? So you have to multiply this. Let's say you have, let's do the inverse transform, whether it's working or not. So I want to get back this. I want to get back my original E in the Cartesian coordinate. So how will do that? That E x, E x, E y, and E z in the Cartesian coordinate. So need to multiply this rotation matrix. So in this case, what is the
Multiply
rotation?
by both the sides. Multiply by R matrix in both the sides.
D multiply. So you have R matrix. Okay. So and then you have this vector. Okay. That 5 by square root 2 and minus 1 by square root 2 and then minus 1. So if you multiply, then you will get Ex, Ey, and Ez. Okay. So you will get the same result. Obviously, you can test it at your home. Okay. Okay. Cylindrical to spherical. Okay. Now next transform is Cartesian to spherical. Okay. So Cartesian to spherical means basically you have to multiply 2 times. Okay. 2 rotation matrices are there. Okay. So here 2 rotation matrices are involved. Okay. So at first this Cartesian coordinate will be transformed into cylindrical one. So this has been transformed into cylindrical one with this rotation matrix into your cylindrical system. And then this cylindrical system is multiplied with respect to the cylindrical coordinate system is basically multiplied with respect to theta rotation, theta degree rotation of phi axis. So this is theta degree rotation of phi axis, and this is basically phi degree rotation of your z axis. Okay, so this is phi degree rotation of z axis, and this is theta degree. So if you do multiply this, then you will get the resultant transform from r theta phi to ax, ay, and az. Okay, so in this way, and in a similar way, you can do the inverse transform. So for the inverse transform, it is easy. Okay, why it is easy? Because of this orthogonality property. Okay, so basically inverse is basically become this inverse become transpose. Okay, so this inverse of this is basically become transpose of this. Okay, and inverse of this is basically transpose of this. Okay, transpose of this matrix. And if you multiply, then you get the overall coordinate transform from this coordinate to another coordinate system. That from Cartesian to spherical, and this is spherical to Cartesian. Okay, so next thing is vector product, and what does it mean? Okay, so at first I'll discuss about the dot product. So dot product is very well known to you. So dot product basically indicate the projection. Okay, the dot product basically indicate the projection of vector from so projection of one vector into another vector. So projection means basically this is the projection. Okay, so let's say you have a vector v and you have another vector v, u, and the dot product between them is basically projection of v in the direction of u. Okay, so in the direction of u. So in this way, it's to find out the inner product or dot product, you can do this type of you can say vector multiplication. So that is ux, uy, uz, and you can multiply in this way. You can do it. Or if you want to, if you know that what is the magnitude of this vector and what is the angle between these two, then also you can find out that what is the dot product between these two vectors. Okay, so this is another way. Okay, so okay, another, this is very interesting proof, that is basically dot product or inner product is basically invariant of coordinate transform. This we done, so it is very easy to do. Let's say I am doing the dot product of let's say two vector, that is u and v, okay, in the Cartesian coordinate system. Now I can do the same thing, let's say in the cylindrical coordinate system also, or I can do this same thing in the spherical coordinate system. So it can be easily proven. It can be easily proven. This basically transform is basically you can say coordinate transform independent. So this u, so this u vector in Cartesian coordinate can be represented in the cylindrical coordinate in this way. So this is your let's do it the v vector. Okay, so v can be represented as this rotation matrix phi into v vector. This rotation matrix are basically phi rotation in the of z axis into this v vector, and similarly this is basically transpose of this u vector. Okay, so this is basically transpose. So that's why this term is basically post multiplied. Okay, this rotation matrix is post multiplied, and here it is basically pre multiplied. And if you do this product, then because why it's become unity, because they are orthogonal. So this is this one, and this is the transpose. The transpose of this rotation matrix and the rotation matrix is basically equals to unity matrix. Okay, so because they are orthogonal. Okay, and similarly, the same way you can prove that the same dot product is also valid in the spherical coordinate also. Okay, so now next comes to the cross product. So for that, I want to show you one animation was there. Where it is? In this one. Okay, this one. So what does it the cross product mean? Cross product means basically the area of this triangle. The cross product is basically the area of this triangle, and the direction of the area is the direction of the vector. Okay, the cross product means basically you have a vector and b vector. Okay, so a vector and b vector, and then the cross product of a cross b means basically the area. Okay, so a cross b is basically this area of this area of this you can say or 2 times of the area. Okay, so 2 times of the area of this triangle. Okay, triangle form, or you can say this parallelogram. Okay, so this is the area of this parallelogram, and the direction is basically the way it's rotate. Okay, so basically the way the screw rotate. Okay, so the way, so let's say a cross b means basically this way. Okay, so the a cross b means basically this way. It is basically in z direction. Okay, so x cross y is basically in the z direction. Okay, so you can see. So this is my x, this is y, and this is my z direction. So direction of the area is basically that which one is projected on which one. Okay, so how this rotation has been done. Okay, so based on that, the direction basically defined. This is the meaning of the cross product. Now, to find out the cross product, there are two ways to find out the cross product. Okay, so first one is this one. Let's say I want to find out the cross product here. Okay, this is one method, and there are actually two methods are there. So let's say I want to find out, let's say A cross B, that is basically you have x hat, y hat, and z hat. Okay, and you have ex, sorry, ax, ay, az, then you have b x, b y, and b. So it is basically similar to the way you do determinant of a matrix. Okay, so it is similar. Okay, so that is x is equals to ay b z. So this way minus this minus a g b y into x cap plus, so instead of plus we can write minus, or we can do in the other way. So let's write minus. It is better way. So minus ax cross bz, ax bz, and az bx, az bx into y plus the last one x ay, ax by minus ay b x in the z direction. So this is one way. This is one way to find out the cross product. The another way is basically by matrix multiplication. Yeah, this way. So if you want to do A cross B, so you have to write down the A cross. How the A cross is formed? So A has two components, 1, 2, 3. Okay, then this matrix is basically this way. It is written by this way. So it is, you have it has some property. Okay, so this matrix is basically, you can say skew symmetric. You know what is skew symmetric? You take transpose and negative, that is equals to the same matrix. Okay. So you can see it is basically skew symmetric, and if you multiply them, then you can get the cross product. So we will discuss in the next class, because time is up for this class. And in the next class, I will discuss about the how this cross product is coming, and using matrix multiplication also you can do the cross product of any two vector. Okay. So goodbye for now. See you in the next class. So if you have any doubt or query, please let me know. Okay.